Okay, so our next speaker is Maria Chara from the National University of the Littoral and CONICET, I believe. And her talk is the conorm code of an algebraic geometric code.
Thank you. And first of all, I want to thank the organizers also for this conference. This is my first time here, and I hope it's not the last one. And I also hope that at some point in my life, I will be able to visit France and to visit you all. And so today I'm going to talk about a work that is going to appear soon in Advances in Mathematics of Communication, which is a joint work with Ricardo Podestá from Universidad Nacional de Córdoba and Ricardo Toledano from my university, both in Argentina. And I'm going to go through the first part really quick because through this morning for me and afternoon, evening for you, we have listened about this stuff. What a code is, it's just a linear subspace of fq to the n, where n is the length, k is the dimension, and d the minimum distance. And I'm going to denote that by an NKD code. And so I'm going to work with AG codes, and this is what Beth said. She was talking about codes defined using points on a curve. In my case, I'm going to use places on a function field, which is exactly the same, but I'm more comfortable with this notation. So I'm going to work with a function field f over a finite field fq. And I have to pick n rational places, which are places of degree 1. You can think on points if you want, rational points on the curve. And to make a divisor d, which is the sum of these rational places. And I have to pick also another divisor g, such that the pi's are not in the support of g. So now the code words in my codes are going to be, well, the evaluation of functions in the Riemann-Roch space of the divisor G. And in this sense, this f of pi's denotes the residue class modulo Pn of f. Here, the places are maximal ideals. And since I'm taking rational places that is of degree 1, these things live inside SQ. As Beth said, this is a generalization of Ritz-Solomon codes, because we are not only having more points, but we are not only having polynomials here, but rational functions. But taking care that the poles of these functions are bounded by the ones that are in G. And so it is well known that the parameters of these codes are, well, the length is obviously the degree of D, is the amount of places that I'm taking. The minimum distance is greater or equal than n minus the degree of g. This is because of the amount of coordinate that can be 0. And the dimension is the dimension of the Riemann-Roch space of G minus the dimension of the Riemann-Roch space of G minus D. So if we have that the degree of G is less than n, that is what we call a moderate AG code when this happens. Then we know that the degree of this divisor is going to be negative. So this part is 0, and the dimension of the code is the dimension of the Riemann-Roch space of G. And by the Riemann-Roch theorem, we know that this is bounded by below by the degree of G plus 1 minus the genus of the function field f. If in addition we have that this happen, when this happens, we call that the code is a strong H code. Then we have the equality here, and we have the exact dimension, which is the degree of G plus 1 minus the genus. So what we did is to use the conorm divisor to obtain another H code when we start from one H code to obtain another one in an extension. Here, we are thinking that we have f, our function field over fq, and we have a finite field extension f prime, that could be considered over the same function, the same finite field of another fq of t. And we are going to use, well, this is finite. We are going to use the conorm divisor, which is if I have a place here and I have all the places in f prime that are over p, then the conorm divisor of that place p is the sum of all of these places in the extension f prime multiplied by the ramification indexes. And if I have a divisor, which is a finite sum of some integer times some places, then the conorm of this divisor is just the sum of those coefficients times the conorm of the place. And so what we did is to start with an HG code over FQ, and this is related with a function field f. So my places p lives in f, and g also is a divisor of f. And we choose an extension f prime such that all the places above my places in the support of D are rational. And we now have this conorm code, which is, well, for G, I will use the conorm of the divisor G. And as the divisor D, I'm going to sum all of the places above all the places in the divisor D. You can think if in D you have, for example, all totally splitting places, then you sum all of that, and that's the conorm of D. Yeah, but that's not necessary. We are just taking all of them, but this is exactly the conorm of D if the places in the support of D are totally splitting. And what we have is that since the Riemann-Roch space associated to G is inside the Riemann-Roch spaces of the conorm of G, then we have that our original code C is a subcode of the conorm code. So what about the parameters of this new code that we are constructing? So now we have our original HG code with parameters N, K, and D. And the conorm code has parameters N prime, K prime, D prime. And of course, the length of this new code is the amount of places that I have there in the extension, and it's bounded by N and N times M, where M is the degree of the extension F prime over F. If all the places in D are totally ramified, then N prime is going to be N. And if all the places in D split completely in F prime, then we are going to have N times N prime. The minimum distance is bounded by this quantity. This is just degree of G prime. And if our new code is a moderate G code, then we have this bound for the dimension. And using Hurwitz formula for the genus, this denotes the genus of F prime. If we use Hurwitz formula, then we can get this expression for the bound of the dimension of the new code. And here we are having, if the original code was a strong HG code, then this is exactly the dimension of the original code. And we can see that if we want to have a greater dimension, then we need to have poor ramification in order to have this degree of the difference very, very low. So remember that this is more or less counting the ramification in that extension. So our first thought was to think, well, what happens if we have no ramification at all, if we have unramified extension? Well, in this case, here I'm using f prime and f over the same function field fq. We are having q here, f, and then f prime. And in this case, it's easy to see that if the original code is a strong HE code, that means that the degree of the divisor G is bounded by these quantities, then the conorm code, it's also a strong HE code, and vice versa. If we have that the conorm code is a strong HE code, then the original code is also. And in this particular case, we can see that the dimension of the new code is m times the dimension of the original code, but the information rate R, remember that R is the quotient between K and N. In the new code would be K prime over N prime. It's the same. So I'm not having much at the end. But if in addition we have that the minimum distance is exactly this, remember that we always have that this is bounded by below by n minus degree of g. If we have that the equality holds, then the minimum distance of the new code is greater or equal than m times d, and the relative minimum distance is greater. In the examples that we made, we get exactly the same relative minimum distance, but we just made not many examples in unramified extensions. And an interesting feature of unramified extensions is that if we are considering extensions over the same function field, over the same finite field fq, and we also have that the degree of that extension is coprime with q, then the conorm code of the dual code is exactly the same as the dual of the conorm code. Actually, we think that this could be true in a more general setting, because what we have to prove to have this equality, what we have is that the dual of the conorm code can be represented as this. With here I have the divisor of Weil differential, and the conorm of the dual has this representation where here I have the conorm divisor of the Weil differential. So if we can prove that these two things are the same or equivalent, then we will have that's whole in a more general setting. But it's not true in general, because we have an example starting with a Hermitian function field where these two things are different. So we may have the equality in a more general setting, but not always. And to end, I want to mention about cyclic codes, that we start studying these conorm codes because we were trying to classify some cyclic HG codes. Remember that the code is cyclic if it's closed under the cyclic shift of coordinates. That is, if I have this word in C and I shift this Cn to the front, then I get another word in C, and if I continue doing that, then I get other words in the code also. And what we prove is, well, first, if I have a finite extension such that all the places in D are totally ramified places in F prime, then if the conorm code is cyclic, the original code was cyclic too. And if I ask a bit more, that is, if F prime over F is Galois, and also if M is coprime with Q, or if Q divides M, and support of D has only totally ramified places, Then my new code, the conorm code, is cyclic if and only if the original code was cyclic. And in the proof of this theorem, what we can see is that actually it's not only that if one is cyclic, the other one is cyclic too, but what we get is that they are actually the same code. So in the case that we are using Galois extensions with totally ramified places in the support of D, and this hypothesis on the degree of the extensions, we are getting a different representation in a higher genus of the same code. And we could prove with this that some very well-known codes can be represented as conorm codes, such as repetition codes, or some codes that we call Hermitian codes coming from the Hermitian function field. Also, Reed-Solomon codes can be always represented as conorm codes because they are cyclic codes. So I can get a representation as an AG code and then construct an extension such that all the places are totally ramified. And so I could get a representation of Reed-Solomon codes as conorm codes. And what's next is try to see if this construction may be useful or not to construct some example of locally recoverable codes. I'm just starting to study about those codes. And since in many construction, what you use is a divisor D with places that split completely, then it is one of the cases of these codes, and this may be useful. And another thing that we are not sure, but we hope we could study at some point, it's first we thought that having a new representation of the same code in a higher genus could be useful for code-based crypto. Then Irene told us, well, no, because we proved that they are not secure, even if you are in higher genus. But maybe, since the problem is not completely settled because we can use subfields of codes, maybe we could manage to do something with these conorm codes or not. If someone has any recommendation for me or want to join me studying more, I will be really glad to do it. And thank you for your attention.